Hello students, today we do magnetism, permanent magnetism in a crispy way. So first, what's a magnet? Magnet is a stone which has attractive property. In ancient times, stones which attract small pieces of iron were called magnets. Modern time, magnetism interaction between moving charges or currents. Suppose a charge is moving through a wire, that we call it as current, then around it a magnetic field will be created. That's a modern approach. The old approach is some materials attract iron pieces, that was called magnetism. Current carrying wire produce a magnetic field around it. Straight wires produce dispersed and weak fields, whereas a circular coil will produce a strong field because all the field passes through its center. Why only some substances are magnets, not all? That is a question. Answer lies at atomic level. 1. First point is revolving electrons means currents. These currents produce magnetic field which are cancelled by oppositely revolving electrons in the same atom. So whenever we have a paired electrons, one electron revolve clockwise, other electron revolve anti-clockwise. So the magnetism between them gets cancelled. If one atom had a permanent magnetic moment, number of electrons are at least one are not paired electron, so the atom is permanently a magnet which possesses magnetic moment. But atoms are, once it form a molecule, the molecule may not have magnetic moment. If molecules have permanent magnetic moment, a group of molecules termed as domains may not have permanent magnetic moment. Means the magnetic moment created by one electron may be cancelled by other electron, one atom may be cancelled by other atom, one molecule may be cancelled by other molecule, or group of molecules may be cancelled by group of other molecules. That's why wood, rubber, plastic, many other things may not be magnets. So iron is also not a magnet, but it can be magnetized. So ferromagnetic materials like iron, cobalt, nickel has domains with strong permanent magnetic moment. Just by aligning these domains, strong magnets can be produced. One is called single touch method, where we keep a bar magnet and rub it continuously like this, and we make one pole to be south and other pole to be north. That we call it as single touch method. Double touch method, by rubbing with two magnets. We have two magnets, one magnet is kept like this, we rub like this. So this side we make it north pole, this side we make it south pole like that. That's called double touch method. Electrical method, we take a magnetic material and wound round a coil and send direct current through it. We should not send alternating current. Alternating current will demagnetize it. Wounding a coil and make the rod will get magnetized. So by single touch method, by double touch method, by electrical method, you can make a magnetic material like iron as a rod magnet. How can we demagnetize it? How can we de-align those molecular magnets? That is by heating, that thermally agitating the molecules, by dropping repeatedly. So if you purchased a new magnet and if it has been dropped multiple times, it loses its some part of magnetism. By passing alternating currents, we can demagnetize a magnet. That is by disturbing the alignment of molecular magnets inside. This is about introduction of the magnetism. Now we will go to the properties of magnets. Every magnet will have two poles. North pole now onwards we call capital N and south pole capital S. So there will be one north pole and one south pole. Distance between these two poles we call length of the magnet. So distance between the poles north and south is called length of the magnet, which is 5 by 6 times of geometric length approximate. This is given in the textbooks, but it's not to be taken very seriously. We make measurements from center of the magnet. So length of the magnet is represented 2L but not L. So we measure length from center to one pole, center to other pole. This is L and this is L. So length of the magnet, that is distance between the poles, we take it as 2L. So if the length of magnet is given centimeters, 10 centimeters, then 2L is to be taken 10 centimeters, but not L to be taken as 10 centimeters. That you remember it. Next is pair property. If we cut a magnet, each piece acts as magnet up to atomic level with two poles, north and south, like heads and tails of a coin. Monopoles don't exist. For example, this magnet we cut into two pieces. This is north, this is south. We expect in the center nothing, but at the center again a north pole will got developed. So again you cut like this, you get north pole. Like that up to atomic level we get two poles, like heads and tails of a coin. Suppose clockwise for one person is anti-clockwise for other person. So electron spinning clockwise from one side is south pole, for other side it is north pole. So poles always exist in pairs. You don't have monopoles or single poles. Coming to terrestrial magnetism, Earth is a huge but very weak magnet. Weaker than bar magnet in our physics lab. Suppose you have a bar magnet that is much stronger than Earth, because while using compass we see north and south direction of Earth. You must take care that no magnets are nearby it. For example, a small magnet is on the table, then the compass will not show Earth's north and south direction. That will be influenced by the small bar magnet in your hand. Reason behind terrestrial magnetism is expected to be some molten fluid that we call it as lava. It is an ionic form inside the earth crust, and due to rotation of earth, the charge of the lava which is in rotation creating the magnetic field. So that could be a reason for very weak terrestrial magnetism. Earth is very big but it's a very weak magnet. Next comes directive property. Suppose you have a magnet and you suspend it freely, then it turns and finally aligns itself in north and south direction of earth. Directive property. A freely suspended magnet aligns itself parallel to geographic north and south direction of earth. This property is used in construction of compass. Geographic north is magnetic south and magnetic south is geographic north, vice versa. Because like poles repel, unlike poles attract. So suppose magnet is showing this pole is a north pole, means it is showing north of earth, but magnetically this is a south pole, that is painted red. This pole, backside pole, is showing south of earth. This is magnetically north pole, but it is showing south pole of earth. That is what geographic north is magnetic south and magnetic north is like that. Now coming to important terms related to magnet. That is, first one is magnetic moment. Magnetic moment in permanent magnetism is defined as pole strength of one of the pole multiplied with distance between the poles, that is length of the magnet. Magnetic moment is defined as product of length of magnet and pole strength. Now pole strength is measured in ampere meter and length of the magnet is measured in meter, so you will get ampere meter square. But first of all, how it is ampere meter, you have to go to electromagnetism. According to electromagnetism, current carrying loop with having area A with number of turns n is a magnetic moment. So whatever magnetic moment we defined it here, this we have defined electromagnetically. So electron revolving in a circle constitute a current, span some area. Otherwise, a circular loop of current, for example this is a wire and this I made a loop, this loop carries current, then that current into this area gives you magnetic moment. Clockwise direction sense is the south pole, anti-clockwise sense is the north pole. So current is measured in amperes and area is measured in meter square. So ampere meter square is the SI unit of magnetic moment. The first law in magnetism is Coulomb's law. That is Coulomb's law of electricity is extended to magnetism. Force of attraction or repulsion between the two poles is directly proportional to product of pole strengths. Don't read it as masses, they are pole strengths. And inversely proportional to square of distance between them. A proportionality constant mu naught by 4 pi is inserted. It's an empirical constant and mu naught value will be 4 pi into 10 to the power of minus 7. If you put that in the numerator, 4 pi gets cancelled, so the constant will be 10 to the power of minus 7 Henry per meter. So now comes the question, what is permeability? So ability of a medium to allow magnetism through it. For example, if we have a magnet, in between some material is being kept, then the iron pieces here above the material, how much they get influenced. In presence of some materials it influences more, in some presence of other materials influences less. So permeability we define as permittability. So if medium permits magnetism more, then we say it has more permeability. If the medium permits less of magnetism, then we say it has less permeability. And medium like air or vacuum will have permeability which is mu naught, permeability of air or vacuum, whose value is been given here. Next comes magnetic induction field strength B. force acting, suppose this force, if you take one of the pole strength here and one you call it as source pole and other you call it as test pole. So the force acting on a test pole kept at the place is the magnetic induction field strength at that place, given by mu naught by 4 pi m by r square. This m is the source which is producing this field, and another m is the test, F by m you can write it as. That is been testing that existence of magnetic field. Magnetic induction field strength is defined as force acting on a unit north pole dependent on medium and kept at that point. Now comes, apart from induction field strength, there will be intensity field strength, because the matter which is permitting the magnetic field is also having some influence on the magnetic field. Induction field is dependent on medium. Intensity field is only due to the source magnet. Intensity field strength is defined as 1 by 4 pi times of m by r square, that is force per unit test pole irrespective of the medium. Intensity, see there, induction field strength is defined as force per unit north pole. Intensity field is defined as force per unit north pole. This is dependent on medium, this is independent of medium. So a magnetic pole creates H and surrounding medium is mu, then the combination gives you induction field strength. A magnet creates intensity field H, surrounding medium is air, then at that point induction field strength is B naught. Like this we have to study. Next, permeability of free space is permitting ability of air or vacuum to allow magnetic lines of force to pass through it. Now that any other material, iron, cobalt, nickel, copper, bismuth, water, permitting ability we compare with air. That ratio we call it as relative permeability, that is called mu r. Relative permeability into, this value will be given in the examination. Relative permeability into permeability of air or vacuum gives you permeability of the medium. Now we define two more important quantities regarding magnetization. Intensity of magnetization. When we magnetize a material like iron, how much magnetic moment it has acquired per its unit volume. Magnetic moment is ampere meter square by meter cube. You will get ampere per meter. That is called intensity of magnetization. Next we define magnetic susceptibility. How much we have applied and how much it got intensified. How much we applied and how much it got intensified. That ratio is called magnetic susceptibility. So intensity of magnetization is defined as magnetic moment acquired per unit volume. Magnetic susceptibility is defined as the ratio between intensity of magnetization to intensity of applied field. These two is a ratio. We call it as chi, susceptibility, and it is unitless quantity. Now when I take a magnetic material and keep in the external magnetic field, say iron in the magnetic field, then domains, the group of molecules having permanent magnetic moment, start aligning themselves in the direction of field and create a field of their own. So you are giving external field, and the magnetic materials which are aligning, they are also magnets, they also align themselves in the direction of field. So net field, whatever is being created because of this magnetic, is applied field plus field due to those magnets which are aligning themselves. And net field, if I write it as mu, that is including permeability of the medium into H, because it's previously it was in air, mu naught times of H is the applied field, mu naught times, that is in air, so mu naught times of the intensity of the field which is being acquired. This is applied field, this is acquired field. So if you divide throughout by mu naught, mu by mu naught H, sorry, divide by mu naught, you will get mu by mu naught, you take H plus I by H, then H by H is 1 and I by H is chi, susceptibility. So you will get finally, you have to divide with mu naught H. So here you have to divide with mu naught H, you have to divide with mu naught H, you have to divide with mu naught H. Then HH gets cancelled, mu by mu naught gets cancelled, and you get 1. Mu naught gets cancelled, I by H. That comes out to be 1 plus chi. Relative permeability is equal to 1 plus susceptibility. This formula will be useful in future. Now, the magnetic materials can be classified into three types: diamagnetic materials, paramagnetic materials, and ferromagnetic materials. So the cause for diamagnetism is orbital motion of electrons, paramagnetism the spin motion of electrons, and ferromagnetism the cause is formation of domains, group of molecules having similar magnetic moment align themselves in one particular line. alignment in external field. Suppose this diamagnet is kept in external field, it aligns, the molecules will align opposite. Suppose we keep north and south in one direction, the molecular magnets align in opposite direction. That means it dislike the applied field. Paramagnetic moment. Molecular magnets align themselves at the direction of magnetic field. So if they are deviated, if you keep external field, they turn themselves towards the applied field. Ferromagnetic materials align strongly. Same thing what is happening in the paramagnetism will happen in ferromagnetism, more intensified. Whereas in diamagnetism, whatever happens in paramagnetism, opposite will happen. So if whatever is happened here for a solid magnet, if you plot intensity acquired, intensity applied, as it is going in opposite direction, so as we go on increase H value, I value go on decrease. That means due to opposite alignment. So you will get a graph of negative slope. Here, as you increase the applied field, intensity of magnetism gets increased. So you get a positive slope curve, straight line. Here, because this happens more quickly it aligns to the maximum value, then it gets saturated because no more magnetic molecules will be available to align themselves. Here is a very gradual process. So molecules go on, align themselves, go on, align themselves, go on, align themselves. Here this happens very quickly. So it gets saturated. So this is a graph plotted between intensity of magnetization to intensity of applied field, which we call it as IH curves. IH curves. Now, if at all we wanted to plot susceptibility versus temperature, that means how much magnetism is getting, how much the material is getting magnetized as we increase the temperature. Susceptibility is small and negative independent of temperature. That means if you little heat it or cool it, susceptibility is not going to change. Basically it is not susceptible. That is what is called negative susceptibility. Curie's law, susceptibility is small and inversely proportional to temperature. That means if you at lower temperatures, molecules align more. As you increase the temperature, the alignment will not be more because temperature intensifies de-alignment. Applied field susceptible, if the magnet is susceptible, then it want to align in the direction of applied field. Temperature disturbs it. So the susceptibility go on decrease when you increase the temperature. Next, this is called Curie's law. Curie-Weiss law. This is large and positive, and at a critical temperature ferromagnet become diamagnet. So initially when you increase temperature, susceptibility increases. At one particular temperature called critical temperature, this ferromagnet becomes a paramagnet and starts losing. So initially up to one temperature called critical temperature, susceptibility increases. At that critical temperature onwards, the ferromagnet behaves as a paramagnet and susceptibility decreases with temperature. This is called Curie-Weiss law. Here susceptibility is inversely proportional to temperature. Here susceptibility is independent of temperature. Here susceptibility is inversely proportional to 1 by T minus Tc. For iron, 770 is the critical temperature. Up to 770, susceptibility increases 0 to 770. From 770 onwards, further if you increase the temperature, susceptibility decreases. Then iron behaves as a paramagnet, which is actually a ferromagnet. Now coming to relative permeability. It will not permit the field through it. That's why its permeability is compared to air is less. Relative permeability, we compare every material with air. So compared to air it is less. So relative permeability less than 1. This is slightly greater than 1 for paramagnets, and it's very high in case of ferromagnets. I am talking about relative permeability. Now the question is, if at all we have a liquid, how do you test whether it is dia, para or ferro? The test for liquid is you have to pour the liquid in a watch glass. The glass will be in this form, watch glass. Keep the poles far away. Then diamagnetic liquid will run away to the center and far away from magnetic field. If we keep the field near, bring the poles nearer, it run away from the center and occupy the edges. So if you are getting convexity or concavity depending on the distance between the poles, we can identify the given liquid is diamagnet. Similarly, if it is a paramagnet, it loves the magnetism. So for example, if magnetic field is far away, the liquid runs far away. If magnetic field is closer, then liquid comes nearer. So Whatever happens here, quite opposite happens here. In case of ferromagnet, the same thing will happen in a more quickly. So here, when a weak field is applied by keeping the magnets far away, at the center you will have less liquid, and at the far where the edges of magnet are nearer, there you will have more liquid. Similarly, when you keep the field stronger at the center by bringing the poles nearer, then it rises in the middle. This is the way we can test whether the given liquid is dia, para or ferro. Now question comes, if a salt is there, copper sulfate, silver nitrate kind of salt is there, sodium chloride. Now how do you know whether it is dia or para magnets? First you have to dissolve it in liquid, that is in water or hydrochloric acid or nitric acid. Pour it in a U-shaped limb. Now put the magnetic field, one of the limb in the magnetic field. If the paramagnet dislike the magnetism, so it will come down here and rise up here. By seeing that, we can understand the salt soluble in this liquid is diamagnet. In this case, slightly it rises and here it falls. That shows that the given salt is paramagnetic. If the rise is much higher, then we say that the salt is ferromagnet. Now, let us take the examples after testing all these things, solids, liquids and salts. What is what? Bismuth, copper, silver, lead, water, mercury, hydrogen, helium, neon, gold, zinc, antimony, sodium chloride, diamond, these all are diamagnets. Sodium, potassium, magnesium, manganese, tin, platinum, aluminium, oxygen are paramagnets. Iron, cobalt, nickel and their alloys, iron oxide, gadolinium, alnico, aluminum, nickel, cobalt combinations, etc. are ferromagnets. So this is the difference between dia, para and ferromagnetic materials. This is the brief account of magnetism, permanent magnetism, not electromagnetism. Electromagnetism is a separate topic.